Let's discuss the null and alternative hypothesis. And this is a very important step because if you are able to write both null and alternative hypothesis correctly with the assistance of statistical software, you should be able to solve the whole problem correctly. However, if you get this first step wrong, as a consequence, there are many step results would be wrong. So it's key. This is a key step. Now, what is a statistical hypothesis? It's just simply a conjecture about a parameter. We are always gonna test parameter. And the null hypothesis, the notation is HO. That means no difference, no effect, no change. So zero change. That's why we call it null. Null means nothing, and null means zero. That's why we denote it as HO or H0. And because there's no difference, that means before and after it's the same. When it's the same, that means equal sign. Therefore, in HO, it must contain equal sign. The alternative hypothesis, because the null is denoted as HO, so the alternative usually is denoted as H1. And in many books, it's also denoted as HA. A means alternative, but our book uses the H1. Now in H1, it's just as long as it's not equal to. When it's not equal to, it can be larger or smaller or different. So one of those three symbols should be in the H1. So therefore, the H1 always has inequality symbol, like one of those three. And normally HO or H1 or HA is the claim you want to prove or disprove. So this is rule of thumb. Although our book does not always put the claim into HA or H1, in practice, we try to rephrase your conjecture so that the conjecture or your claim can be put into H1. Now, HO and H1, they must be mutually exclusive. That means they cannot overlap. HO does not contain any results that should be in H1. H1 should not contain any results in HO. They just don't overlap. Now, let's look at a few examples before we try to write our own null and alternative hypothesis. We talked about this X sorts method of gender selection in the introduction. So they claim that this method increases the likelihood of having a baby girl. Now, because this is the chance of getting a baby girl, if there's no such gender selection method, the chance would be probably 50%. Probably this is the common sense, right? Chance of getting a baby girl is 50%. Now, with this method, they claim that it increases the likelihood of getting baby girl. That means this chance, the chance of getting baby girl should be more than 50%. So therefore, you see that's why we come up with these two statements, and the HO is the one contains equal sign. If P is equal to 0.5, that means even you with this XOR gender selection method, the chance of getting baby girl is still 0.5. That means this method has no effect, no change. So that's what we just explained in the last page. So no change, no effect, always HO. When this P is greater than 0.5, that means chance of having baby girl is more than 50%. That's H1. So if this happens, that means this gender selection method is effective. Now, if I'm going to draw a straight line here. So in this straight line, this 0.5 is the chance of having baby girl. So without using any method, it's 0.5. Chance of getting baby girl, baby boy, they should be equal. If this method is effective, then chance of getting baby girl should be higher than 0.5. In other words, it's falling. The change will be falling to the right side of this 0.5, the test, the hypothesized value. So because of that, we are going to call this as right tail test. So in other words, whenever you see this greater than, it's going to be right tail test. We are testing whether the unknown parameter is falling into the right side of this tested value. All right. So that's the explanation. Let's take a look at the second one. A chemist invents an additive to increase the life of an automobile battery. The mean life of the battery without the additive is the mean life of the battery without the additive is 36 months. So this is without. Now let mu be the mean life with the additive, because we're talking about mean. Mu is the symbol we are going to use. So here's the hypothesis. This chemist claimed that this additive increased the battery life, right? So therefore, you are going to expect with the additive, this mean life should be longer than the one without the additive. That's why we have mu greater than 36. Now the opposite, the null hypothesis would be mu equals 36. If it's equal to 36, that means with the additive, it's still the same. Therefore, there's no effect, no change. And here, the claim here is better life. Again, this is a right tail test because we see the greater than symbol. Again, if I draw 36 here, this chemist claims that the battery life with the additive is on the right side of the 36. That's why this is called a right tail test. Now another example is this. Here's the question. Will a special type of insulation in-house lower heating bills? So here we are interested in knowing whether it lower heating bills, right? So first of all, the average monthly heating bill is $78. Now let mu be the average heating bills with the use of insulation. Will it lower the heating bills? If it lowers the heating bills, so it will be the heating bill should be on the left side here, right? So that's why we are testing mu less than 78. That's why this is the hypothesis. And mu equals 78 will mean there's no difference. So mu is with the insulation, it is still the same as the common average monthly heating bill. So in this case, HO, you can see that it means no effects, no change. And H1 means it's effective. And you probably see that why this is called the left tail test, because we're testing to see whether the mu is on the left side of the 78. Put it in another word, if you see the less than symbol, that means a left-tailed test. Now, another example is, let's look at this question. Will the new medication have any undesirable side effect? And regular mean pulse rate for the population of interest is 82 beats per minute. And then side effect exists. That means it's the pulse rate is either increased or decreased. So that means side effects exist. That's one way to measure the side effect for this particular medication. Now let mu be the mean pulse rate after taking the medication, because suppose this is 82. After taking the medication, if the pulse rate is increased or the pulse rate is decreased, one of those two occurred, that means there's a side effect. So therefore, we want to the result we want to detect is whether one of those two occur, right? Do you see that those results fall in both sides of 82? Therefore, when mu is not equal to 82, that means it's either lower or higher. That means the side effect. That's how we come up with this hypothesis. And mu equals 82, that means no effect because there's no pulse rate change. In this case, we call this is a two-sided test because we want to detect whether the result fall in either side. So this is a two-sided test. Now, so this is the summary: one-tail or two-tail test, one-tail and two-tail test. A two-tail or two-sided test, this is the characteristic. You see the not equal to symbol. The one-tail or one-sided test, if you see the less than, it's left tail. If you see the right greater than, that means the right tail. All these symbols, they fall into the H1. The HO is always going to be equal, no exception. So previous one, it's testing proportion. So you can see that the one tail, two tail is just, how can you determine? It's really just the sign in the H1. Okay. Now let's take a look at a few sample hypotheses and let's decide whether they are valid or not valid hypothesis. So this is the first one. HO is mu is 12. H1 is mu is greater than 10. Are these two valid? The answer is, you can pause it now and think about it for a moment before you resume the video. Answer is not valid, and the reason is this. Now these two numbers, they have to be the same. They have to be the same because they have to be mutually exclusive. Mu greater than 10 already contains 12, right? So this doesn't make sense. And let's go back quickly. Let's go back to both. If you can see that the value in the hypothesis, they must be the same value, right? They must be the same value, okay? So that's why it is not valid in this example. Let's take a look at the second one. Valid or not valid? Please, you should pause the video if you need a little time to consider. In this particular one, it is not valid because the equal sign must be in HO, and the not equal sign, in this case, the less than symbol must be in H1. It cannot swap. It cannot be swapped, so it is not valid. Now the next one, again, pause the video if you want to have a moment to think about it. Here it says x bar is equal to 0 and x bar is not equal to 0. This is good, equal sign in HO, not equal sign in H1. But x bar means the sample mean. We never test sample. Once you have a sample, you already know its result. You don't need to test it. We are testing population parameter. So in this case, sample mean symbol should not be used here. Population mean, mu, should be used. So it is invalid. Now, for this particular one, same reason, p hat is the symbol for proportion, sample proportion. So it's for sample. It's not for parameter population. So we need to change this to p, the population proportion, to make this valid. Now this one, if you look everything, it is a valid one. This is a equal sign in HO, the less than symbol in H1. Both are -6. Both have the same symbol mu, which is correct. Let's look at this one. If you look carefully, there's an equal sign here, and there's another equal sign here. We say the both hypotheses must be mutually exclusive. They cannot overlap. In this case, they have one overlap. therefore it's not valid. If you have to correct it, you should not use the equal sign here. Get rid of this equal sign. And let's look at the next one. So in this case, you can see that not equal sign is in HO, equal sign in H1. This is incorrect, right? Equal sign has to be in HO and not equal sign has to be in H1. So that